Here is some pure climate dynamic stuff that we often tend to ignore because we are so focused on climate change. This is a nice group of people who wrote this paper. Dave Thompson, I think Jim Harrell's name may be there as well. We know that the western boundary currents are a very critical part of the whole thermohaline circulation. There have been some studies showing that the sharp fronts generate some response in the atmosphere. In general, there is this debate about whether cold SSTs at high latitudes do anything to the atmosphere. The atmosphere clearly responds to warm temperatures in the low latitudes, and it's known that the western boundary currents have a climatological impact. For example, the Gulf Stream is a good story of how the same latitudes on North America have very different climate compared to the latitudes in European parts because of the Gulf Stream, the heat transport, the ocean-atmosphere interactions, even though Richard Seeger put some details that it's not the Gulf Stream, it's the waves from the Rocky Mountains, but that story has kind of died away, I guess. So here is the summary that the authors themselves provide in Nature, and then we'll look at some figures from the paper itself. I'm still having some allergy issues. Oceanic western boundary currents modulate local climate variability. So that's the headline. This study reveals that variability in sea surface temperature in key oceanic surface currents has a distinct and robust influence on the local atmospheric circulation, affecting precipitation and vertical motion, the rising and sinking of the air. The findings enhance our understanding of how ocean dynamics shape climate variability outside the tropics. This has always been an issue that has persisted for a long time. What is the question? Understanding the influence of oceanic western boundary currents such as the Gulf Stream and the Kuroshio currents, which are the most famous, on atmospheric variability has widespread implications for weather prediction. These currents are known to influence the mean climate, as I mentioned. However, their role in driving climate variability, that is changes in the mean climate, is less well understood. Previous studies have generally concluded that month-to-month variations in sea surface temperatures in such currents as measured by satellites have a relatively small effect on atmospheric variability compared with the internal atmospheric dynamical processes especially the eddies that are trying to do the northward heat transport become more and more dominant as we go north. Here we explored the signature of the western boundary currents in atmospheric variability using an innovative method focusing on local linkages rather than large scale effects. So they go to SST precipitation and lapse rates and so on, and they use the observations and modeling here, as we'll see. The analysis probes the covariability of atmospheric vertical motion and precipitation with SST over the main western boundary currents of both hemispheres using high resolution reanalysis, satellite observations, and numerical model output. The key novel aspect of the analysis is that it focuses on the month-to-month covariability between SSTs and the atmospheric circulation at local scale. Typically, if you go look for large scales, then the local scale of the SSTs and the large scale dynamics seem disconnected, but local evaluation analysis seems to give deeper insights. The approach contrasts with that used in most studies of atmosphere-ocean interactions, which have focused on the relationships with SSTs averaged over broad spatial regions. The findings indicate that local atmospheric variability, particularly of vertical motion and precipitation, co-varies with local SST anomalies over the western boundary currents. Warm conditions over the boundary currents lead to anomalous rising motion, increased precipitation, and vice versa, as we'll see. The local atmospheric response mirrors the complex spatial pattern of SST variability in these regions. Jumping ahead, the troposphere is the lowest layer of the Earth's atmosphere, containing most of the clouds and weather. Our analysis indicated that the changes in the atmospheric flow extend throughout the troposphere. Relationships between SSTs and atmospheric vertical motion and precipitation are consistent across the main western boundary currents of both hemispheres. This suggests a robust mechanism by which oceanic processes influence local climate variability, potentially through heat flux from the ocean into the cold wintertime atmosphere, thus promoting atmospheric convection. So that's the main story. What are the implications? Sorry about that. The findings suggest that western boundary currents play a more important part in climate variability than was previously recognized. By demonstrating a strong local atmospheric response to SST changes, the study offers insights that could improve weather forecasting and climate modeling as well, particularly in the regions influenced by the ocean western boundary currents, the Gulf Stream, Kuroshio-Oishio, Agulhas, Brazil, Malvinas currents, and of course there is also the East Australian current, which is not mentioned here. The research is restricted to analysis of local atmospheric responses and monthly averaged data. The implications of the results for the large-scale atmospheric circulation or longer time scales remains unclear. So there is always the issue of what climate change is doing to the western boundary and what that may mean for local weather and climate, etc. Future research should explore the underlying dynamics of the observed relationships and their influence on the larger scale atmospheric flow. So the main paper is titled Signature of the Western Boundary Currents in Local Climate Variability. Just to make some additional points, let's just skip ahead and look at the figures. I don't want to read much more text. We already got the main points. So look at the figures to make sense. So here is a Gulf Stream, Kuroshio-Oishio, Agulhas on the Indian Ocean side coming into the Atlantic, Brazil Malvinas in the southern Atlantic, and so on. Observed signature of the western boundary currents in climatological mean, vertical motion, and precipitation. So here is vertical motion, and let's just read the title, caption properly. A to H, the wintertime mean of SSTs, so there is a seasonality at which the responses are looked at. The wintertime mean of SSTs in contours overlaid with mean atmospheric vertical motion at 850 hectopascal, which is the top of the boundary layer, and in ACEG, and that's in ACEG, and spatially high pass filtered precipitation in BDGF. The vertical motion is smoothed with a 3-point which is about 75 kilometers spatial running mean for display purposes only. Contours range from this and that, and results are from ERA 5 data set. So you can see the vertical motion and the contours of sea surface temperatures are highly co-located in space for the Gulf Stream, and precipitation is also co-located with the SSTs and the vertical motion, which is not surprising. The relation, close relation between the SSTs and the vertical motion and precipitation are surprising and new. Okay, so this is the same thing in Kuroshio-Oishio. This is the same thing in Agulhas and Brazil Malvinas. You can see the magnitudes are different when you come to the southern hemisphere. They are not as strong in terms of the coherence in time and space in the southern hemisphere, but nonetheless the relationship exists. The second figure is looking at the observed signature of the western boundary currents in month-to-month variability in vertical motion and precipitation. So it's showing standard deviations of the grid point SST anomalies, grid point vertical motion anomalies at 850 hectopascal regressed onto grid point SST anomalies, grid point precipitation anomalies regressed onto grid point SST anomalies. Anomalies are defined as departures from the long-term mean seasonal cycle. You can look up the methods. The rows correspond to the 4 western boundary currents of interest. Results are based on monthly mean data from ERA 5. So you're definitely talking about low frequency as well, and not just high frequency daily responses and so on. So Gulf Stream SST, very clear signature. These are, make sure, variability, standard deviations. Are they small, large? Well, they are significant, right? And vertical motions, quite coherent response, and in precipitation as well. Same for the Kuroshio-Oishio, and Agulhas now appears much more clearly than it did in this figure. So it just depends on what you look for. The variances, variabilities are closely related, and similarly in the Brazil Malvinas current off of South American east coast. Okay, so looking at the vertical motion variability associated with SST variability in the 4 western boundary current regions. Sorry about that. Vertical profiles of the area averaged of grid point regressions between vertical motion and SST anomalies for the indicated regions. There are some details. The associated confidence level based on student's t-test using 88 degrees of freedom, etc. So obviously there is high confidence as you come closer to the lower levels, where the driving has to happen from the SSTs into the atmospheric variability. So you can see that there is vertical motion profiles very clearly being dominated by surface variability and falling off to 0 in the upper atmosphere, which is not surprising. So average of grid point regression between vertical motion and SST anomalies for the indicated regions, which means the influence of the SSTs is quite coherent well into the free troposphere beyond the boundary layer, right? So there is real driving of the atmospheric motions and precipitation by the ocean in mid latitudes, which is really the new result here. Simulated signatures or signature of the western boundary currents in a high resolution coupled ocean atmosphere global climate models, again looking at standard deviations of grid point SST anomalies and grid point vertical motion anomalies regressed onto grid point SST anomalies, and then precipitation anomalies as well regressed. So this is from the model, high resolution model, which is basically effectively reproducing this relation between the western boundary current. So when we say western boundary current, obviously it has all existence from the deep tropics into the mid latitudes. We are mostly talking about the separation region here, where it peels off the coast and comes into the open ocean. That's the region we are looking at in, that those are the dominant regions being considered here, and not necessarily along the pathway, even though you can see some correlations extending into the lower latitudes of the western boundaries as well. Okay. Finally, simulated signature of the western boundary currents in low resolution coupled atmosphere ocean global climate model. The standard deviations, again we are looking at the same points, and you can see that the relation is not very robust at all, right? So high resolution features of the SST signature is very critical to capture, even at low frequencies, the atmospheric response locally, and you expect that any local vertical motion precipitation response and the heat release is going to have some impact on the larger scale circulation. But if you just look at large scale circulation, especially from coarse resolution models, you are not going to find the relations that these people are reporting here. So the physical processes that link the climatological mean SST field to the atmospheric circulation include a range of meso and synoptic scale phenomena. For example, in the long-term mean, regions of relatively high extratropical SSTs are marked by locally enhanced precipitation not only during the passage of atmospheric frontal systems, but also due to perturbations in surface pressure and vertical mixing that can arise in the absence of frontal passages. So the fronts in SSTs themselves can have high pressure over colder side, low pressure over warmer side, and then vertical mixing. This has been discussed by other people in terms of frontal responses, whereas here they are talking about vertical motion in and precipitation as opposed to just these wind responses. And then the question is whether the wind response reinforces the sharp front or diffuses it, and so on and so forth. Okay, so atmosphere obviously has at these latitudes a lot of baroclinic instabilities, eddies, storm tracks, and all those good things. So generally the focus has been on atmospheric dynamics, internal instabilities of the atmosphere. Here the idea is to say the ocean does do something. The close correspondence between the structure of the atmosphere-ocean interactions in the long-term mean, as shown in previous work, and in the context of month-to-month variability as shown here, suggests that a similarly diverse range of physical processes act to couple SST variability to the overlying circulation on both time scales. Okay, so you want to understand the long-term low-frequency rectifications like the different climatologies of climates on the western side of the western boundary current, on the eastern side on land, they're mostly, right, Canada versus Europe, let's say. Okay, so the signature of the SST field in monthly mean precipitation arises from changes in daily mean precipitation across a range of amplitudes, which further suggests that a variety of physical processes underlie the relationships observed on month-to-month timescales, and they have lots of supplementary material that you can look at. So this is the low frequency stuff that we already looked at. Finally, to conclude, the complex structures of SST variability in the western boundary currents are largely driven by ocean dynamical processes, internal variability of the ocean, the nonlinearities, the breakup into eddies, and so on. Hence, the patterns of covariability between grid point variability in the SST field and the overlying atmosphere indicated here may be interpreted as the extratropical tropospheric response to ocean dynamical processes. So it's not just the lower part of the atmosphere, the response is penetrating into the free troposphere, as we saw with the correlations. Depth of the atmospheric response is important, of course. Linear theory indicates that lower tropospheric heating anomalies are generally balanced by vertical motion in the tropics, but by horizontal temperature advection in the extratropics. Okay, read that again. Linear theory indicates that lower tropospheric heating anomalies are generally balanced by vertical motion in the tropics, so forced ascent, expansion, cooling, clouds, precipitation, convection, the whole shebang. Whereas in general we assume that horizontal temperature advection in the extratropics dominates with not much vertical response, especially into the free troposphere. As such, the heating associated with tropical SST anomalies is readily communicated to mid-upper troposphere, where the resulting circulation anomalies can be communicated over vast distances, which is the entire global forcing by the West Pacific warm pool, for example, Western Pacific warm pool. Whereas the heating associated with extratropical SST anomalies is more readily balanced by local circulation anomalies that are restricted to the lower troposphere. The depth of the extratropical atmospheric features indicated here is reminiscent of that typically found in association with the tropical SST anomalies. This suggests that SST variability in the western boundary currents may drive variations in the upper tropospheric circulation over regions far removed from the SST forcing. The amplitude of the remote response will depend on the spatial coherence of the precipitation variability. So that heat release in the atmosphere is going to be very important for how far the influence can reach from the SST into the free troposphere. The spatial coherence of the local precipitation response and the resulting non-local signatures in the atmospheric circulation is a focus of ongoing research, which means you can expect another nice paper from this group. Okay, so I think they're all sitting in Colorado State, Jim Harrell, David Thompson, and the co-authors. Okay, so let me leave this here. It's a nice topic. Not climate change as yet, because they are mostly climate dynamics people, atmospheric dynamics more specifically, but I'm sure they will eventually try to see what this means in terms of oceanic response to climate change or anthropogenic forcing, and what it means to the air-sea interactions, and so on and so forth. Okay, let's meet in the next topic.